So we have here a compound bar in parallel setup, and all that simply means is that our materials will be running alongside each other. Now this is meant to be a concrete strut, so you would see a lot more concrete, but I've set up this image because I wanted you to see that the bars actually run alongside each other. Now it's a 2mm concrete strut, and it's reinforced using steel rebar. And what we have a force of 150 kilonewtons, so that's for the F, that's compressive force there. We have the modulus of elasticity for concrete, which is 10 gigapascal. We have the modulus of elasticity for steel, which is our 200 gigapascal. And we also know the dimensions. We know that the dimension for the concrete is 0.2 meter by 0.2 meter, or 200 mil. And we also know the diameter for the steel rebar is 10 mil, and we have 5 of them. So of course our starting point would essentially be to find the area of each of the material. But I'm not just going to do that. I'm going to analyze this thing down to every single step so you can understand what the formulas represent. But just before we get to that part, let's just do the basics. Let's find the area of the materials, and then we get into the analysis. So area for the steel, let's just use A equal. It's 5 of them, so that's why we're having that 5 there. So 5 multiplied by pi times radius squared. So let's use 5 squared there for our radius, and that will give us 392.7 millimeters squared. So that's representing the area of the steel. And then now for the area of the concrete. So for this one, we have 200 by 200. So for this area, when we do our 200 mil by 200 mil, we're going to get 40,000, of course. However, because the steel rebars take up some of the area, we have to remove that. So what we have to do then is to subtract the area of our steel from the concrete. So then final area is equal to our 40,000 minus that 392.7. That gives us our final area for the concrete. So we have the area for the concrete, we have the area for the steel, and we're now going to get into some really deep step-by-step analysis of how to find our direct stress in the steel and concrete, and after that our extension. But just before we do that, I'm really passionate about growing a really rich library of mechanical engineering and mathematics content, and I upload 5 videos every single week, and all I'm asking for is your support. And to do so, please just subscribe to the channel and give this video a like. Now back to the video. So let's analyze what will be happening since this is a parallel setup. So the first thing that you must observe is that the strains will be equal. So whatever strain we have in the concrete, we're going to have the same strain in the steel rebars. And if you can recall, our strain is also in this formula for modulus of elasticity, which is stress divided by strain. So we can rearrange this then to give us our strain as the stress. So we'll have stress in material A over Young's modulus in material A, and those two things should be equal as well. So that should be equal to the stress in B, modulus of elasticity in B. So this is going to be the same effect, the same ratio. So that's the first thing. Now the next thing that we need to also notice is that when the force act, when that external force acts, it will be distributed across the material. So we'll have some of that force distributed across material A, but when we sum the force across A and B, that should give us the same net result. And for the forces, we can substitute our forces with our stress times area formula. So for this one, force can be substituted using stress times area for A, and B, stress times area. So all of these equations that I'm setting out, they will become apparent shortly, because what we're going to do now, we're going to equate the first equation. We can either substitute stress A or substitute stress B based off of this equation that we have up top. And let's say we were to substitute stress A, for instance. Stress A, when we rearrange this one up top here, I'll just highlight that so you see where I'm pointing, that one. Stress A would just be stress B times modulus of elasticity A over modulus of elasticity B. And we can substitute that right there. And that's exactly what we're going to do now to get our formula for force. And this is the final step to get our formula. So force would then be equal to, so we're now substituting our stress A with stress B times modulus of elasticity A, and all divided by modulus of elasticity B multiplied by area A. And that's just going to be added with stress B times A B for area B. Now that's the final formula, and from the looks of things we have stress B that's common to both, so we can just factor out our stress B there, and what we're going to be left with is area A times modulus of elasticity A over modulus of elasticity B, and that's going to plus with area B. So that's the final formula. And this formula, it's flexible. So if we want to find out what, say, stress A is right here, then we could just substitute throughout and just change the letters out from A's to B's. So this is the formula that we'll now use to do our analysis for stress. So let's start then with the stress for material A, which is the steel. So that's our material A. So for this one, we know the force because it's the same force, 150 kilonewtons, so 150 times 10 to the 3. We are trying to find our stress, so that's going to be the unknown in this one, and all divided by. So we got the area previously, and that was 397,607, multiplied by the modulus of elasticity, which was 10 times 10 to the power of 9, and that will be divided by next modulus of elasticity, 200 times 10 to the power 9, and plus area B, which was 392.7. So what we have to do, we just need to simplify this left side, all of that, and use it to divide our stress A. And what that will look like is just 150 times 10 to the 3 equals our stress A multiplied by, when we simplify this now, we get 2,373.1. And all we have left is just a simple division. So it looks complex, but when you put in the values, everything just simplifies to something workable. So this looks like 150 times 10 to the power of 3, and all divided by 2,373.1. So that leaves us with a stress of 63.2 newtons per, I'll use per millimeter square because we didn't convert the units. So what's going to happen now, we're going to repeat the same process here to find out what the stress is for material B. So let's do that now, and this one will be as straightforward. So we're going to use the same formula to do that. So stress for material B, so that's our concrete. So we use the same formula, but we'll just swap out the A's for B. So this time we'll have stress B there. And instead of area A, we have area B. Instead of mod B, we have mod A over B. And that's plus area B. So that's it. It's quite flexible formula. So let's do our substitution. So we have 150 kilonewtons. We're trying to find stress B, so that's our unknown, and we know all of these. So that's going to be 392, and that's going to be plus our 39607. So just like before, we just need to simplify this side, and when we do that, we get what stress B is, which is going to be equal to our 150 times 10 to the power of 3, all divided by the total that we got for that side, which is 4,000. 47,461, and that equals 3.16 newtons per millimeter squared. So that gives us the stress in material A, the stress in material B. Now for the last step, which is us finding the strain or the extension. Now this one, remember that our strain in B should be equal to our strain in A. So we could use either the strain for the concrete or the strain for the steel bar. It doesn't really matter which one we use. So let's say we use the strain in B. Then that's simply just going to be stress divided by modulus of elasticity. So the stress that we just found for B was 3.16 and divided by 10 times 10 to the power of 9. And that will give us a strain of 3.16 times 10 to the negative 4. And the unit there is none because it's just a ratio, this one. So if we were to then find the extension in the bar, the overall extension, so we know the formula for strain is our change in length divided by initial length. So if we were to find the extension, then our extension would be strain multiplied by the original length there. And we know both of those values. So all we have to do is just to multiply them. Our original length is actually 2 meters. So that's what we're going to use. But because we have been consistently using millimeters, I'm just going to convert that into millimeters. So that will just be 2,000 millimeters. And we have an overall change in length of 0.63 millimeters. So that's everything. That's representing our stress in both materials, our strain in the materials, and the change in length. Now, if you haven't watched our compound bar in series, then you should check this video out so that you get the full concept.